In this video, we're going to use the node voltage method to calculate the voltage VO, which is the voltage across this 1K resistor. Now, because we're going to use the node voltage method, the very first thing is to identify all of the essential nodes. We know this is an essential node. We're going to label this node 1. We know this is an essential node. We're going to label it node 2. And we have one more essential node at the bottom here. And we're just going to label it node 3. But instead of me labeling this essential node, I'm actually just going to take it as the reference node. And we know the voltage at this node is going to be 0 volts, right? So we know we're going to be using the node voltage method. So we want the voltage at each node. So I'm just going to write it as V1 and V2, right? So let's start with node 1. We want to write a node voltage equation at node 1. Now, before we even start to write this equation, I want us to notice something. In one of the branches, we have a sole voltage source, which means the value of that voltage source is going to be the value at that particular node. So for node 1, we see we have a voltage source here. And when we look at this, there is no resistor, just a voltage source, which means the value of this voltage source here is the same exact value of the voltage at that particular node. So because the polarity is positive to negative, we're going to take this as a positive voltage. Therefore, we don't even have to write a node voltage equation for node 1. Why? Because we know node 1, the voltage at node 1 is going to equal this voltage source, which is going to be a positive 6 volts. Now, I'm just going to circle this, right? This isn't our answer, but this is very important to us. So we know the voltage at this node because we know the voltage of this source. Now let's do node 2. We know this doesn't have a branch with a single voltage source, so we have to write the node voltage equation for node 2. So we have node voltage at node 2, right? So we're going to assume the current is leaving the node. So when we look this way, we can see we have a current source that's actually going to enter this node, which means we're going to treat it as a negative current, right? So instead of it being a positive 3 milliamps, it's actually going to be a negative 3 milliamps. So we have negative 3 times 10 to the negative 3 plus, we're going to assume the current is actually going to flow this way. So we're going to have V2 minus the reference node, but because it's 0 volts, we're just going to write it as V2 over 6,000. And that's going to give us the current in that branch. Plus, we have the current flowing in this direction here, which is going to be V2 over the equivalent resistance of these two. So we're going to have V2 over 3,000. And all of that equals 0. So when we start to simplify this, we know the LCD is going to be 6,000. So we're going to multiply each term by 6,000. So this is going to give us negative 18 plus V2 plus 2V2 equals 0. When we simplify this, we're going to get 3V2 equals 18. Now we can solve for V2. We know V2 equals 6 volts. So this is going to be the voltage at node 2. So we know both voltages. We know the voltage at node 1 and we know the voltage at node 2. Now to find the voltage at this particular resistor, we can do a KVL loop or we can just do voltage division. Now for the sake of time, I'm actually just going to do voltage division, right? I think that's going to be quicker. So we want to find V0. So we're going to have V0 equals Vs multiplied by R0 over R0 plus R1. We know Vs is going to be the voltage source. In this case, it's going to be V2, which is the voltage at node 2. So we know that is going to be 6 volts. So we have VO equals 6 multiplied by the resistor R0 is going to be this 1K resistor and R1 is going to be this 2K resistor. So we're going to have 1,000 over 1,000 plus 2,000. So when we simplify this, we're going to get VO equals 6 multiplied by 1 over 3 Therefore, VO equals 2 volts. So this is going to be our answer for this particular problem. The voltage VO, which is the voltage across this 1K resistor, is going to be 2 volts. So we found V1, but we didn't really need V1. So that's how these problems work sometimes. But this is how you solve these types of problems.